Okay, let's get started then. Second lecture on EPR simulation. In the previous one, I've shown you how the Hamiltonians differ between NMR and EPR. The assumption is that you are much more familiar with NMR than you are with EPR. Today, I'll focus more on how EPR spectra are simulated in one particular regime, which we have largely forgotten about in NMR spectroscopy, but which is actually dominant in EPR. That is the field-swept spectroscopy. The difference instrumentally is that NMR magnets, by and large, are superconducting now, which makes it rather difficult to sweep the field, certainly in any significant ranges. But NMR spectra are rather narrow. So at most you will see carbon-13 at high field, maybe a couple of hundred kilohertz. So very narrow spectra in a magnet that is very hard to sweep. And these spectra can be excited uniformly by a pulse, hence the current dominance of pulsed techniques, followed by time domain detection, followed by Fourier transform. In this sense, EPR is almost the exact opposite. Most EPR magnets in current use are electromagnets, which are actually quite easy to sweep, from -3 Tesla to +3 Tesla if you have to. Most EPR spectra are very broad. You are talking hundreds of megahertz, multiple gigahertz, and it is therefore impossible to issue a pulse that would uniformly excite that interval. Once excited, it's actually not possible to digitize the corresponding oscillation properly, because you would have to have extremely fine stepping, so 1 over multiple gigahertz is exactly the same frequency in the sampling, and so electronics has problems. There are problems with microwave shaping and so on, and so the dominant method for recording a one-dimensional EPR spectrum is exactly the method that you've been told about when you did basic undergraduate physical chemistry. You shine a particular monochromatic microwave frequency on the sample, and you are sweeping the current in the magnet coils to move the magnetic field around. So in NMR, the field is fixed, the frequency is variable. In field-swept EPR, the frequency is fixed and the field is variable. Now, that introduces a completely different way of looking at the simulations, historically preceding, in fact, what I've talked about previously. And these simulations are logistically much harder, in fact, than the simulations that we have in NMR. And it wasn't until very recently, maybe 2003 or thereabouts, that decent software turned up that does it in reasonable time by extremely cleverly reusing the data from the previous stage that has to go through. Okay, so simulation of field-swept EPR experiments. Because we are sweeping the field, we must expose the field explicitly as a variable in the Hamiltonian. So what we will have is our big Hamiltonian would be B0 HZ, where these are Zeeman interactions, and HZ is normalized for the field of 1 Tesla. So in a way, this is the Zeeman Hamiltonian per Tesla, and then the B0 is our magnet field in Tesla, which scales this contribution to the Hamiltonian. We would have some microwave Hamiltonian, H and W, and it will be modulated with a cosine of some fixed frequency, microwave frequency T. And here we have the usual Lx and Ly multiplied by the G factors and so on, the various scaling factors that you would have in the interaction between the spin and the applied electromagnetic field, plus the rest of it. So H interaction would contain all the dipole couplings, all the hyperfine couplings, all the exchange, all the zero field splitting, and so on. For our purposes today, we don't really care what's inside here. We don't particularly much care what's inside HZ either. The only thing we need to know about is that this is oscillatory, because we will be using perturbation theory results here. We need to know that this scales with the magnetic field, And importantly, what we need to know is that this term here is always much smaller than the other two. So this here is a perturbation to a very decent accuracy. So we would normally be looking at multiple gigahertz, or even hundreds of gigahertz inside here. We would be looking at hundreds of megahertz and gigahertz in here. This perturbation, a couple of hundred kilohertz, maybe a megahertz. In terms of the maximum microwave power, you can realistically output, and so this will always be a perturbation for us. Okay, so what do we do here? Well, the standard flowchart that you are all used to from textbooks of time-dependent perturbation theory. We take the unperturbed Hamiltonian and we diagonalize it. So the unperturbed one is B0 Hz plus H interactions acting on some wave function, returning the energy of the wave function and the wave function back. Assuming we found them, it's a discrete energy spectrum. We should just number these things with n, N, En, and there will be n here as well. I'll just get a better marker here. Let's try the green one. So the procedure of obtaining n and En is called diagonalization. Because if you move it to that basis, the Hamiltonian becomes diagonal. And I will not go into the details of how this is performed. Just take my word for it that if you take the Hamiltonian matrix and you give it to MATLAB, Python, Mathematica, any decent scientific or engineering programming language, it's an elementary operation. It returns you the n and the En, and the operation, importantly, always scales as O n cubed, where n is the dimension of the matrix. So you need roughly that many multiplications to perform this, and you can probably say that when n hits 1,000, this becomes a significant problem, because then you require 1 billion multiplications to diagonalize that matrix. When it becomes 10,000, then it actually becomes rather challenging, and it is essentially impossible beyond that. And so the method I will be talking about today is rather fundamentally limited to about 12 spins. With a very big computer and a bit of ingenuity, you can stretch it to 15 spins. But again, 2 to the 15 and z cube is the number of multiplications that you retain. So 2 to the 12 and then cubed, that's 2 to 36. That's a lot of multiplications. And it scales very steeply from that on. So one health warning here is that applies. Well, of course, then we have our energy wave functions, in this case the vectors. We have our energy levels themselves. Our potential transition frequencies from an energy level n to an energy level k would, of course, be En minus Ek. And the classical questions that you always ask in quantum mechanics from your second year onwards, under our perturbation here, is this an allowed transition? If the transition moment, so n h perturbation k is 0, then there is no transition. The system doesn't absorb the energy. You would not see the transition spectroscopy. If this is non-zero, then various interesting things begin. But our question is, does this equal or not equal to 0? Now, again, I've introduced both time-dependent and time-independent perturbation theory in the previous lectures, so I will simply write down the equation, roughly related to Fermi-Golden rule, for the intensity of a particular transition under an oscillatory perturbation of this kind. So the right way of doing that would be to go to our, I think it's module 2 of this course, and there we just go through the full time-dependent perturbation theory with a cos perturbation, and ultimately we get the following expression. A and K, so the transition probability per unit time from level n to level K is 1 over 4 h bar squared modulus K is h microwave and absolute squared, and then gamma of omega K minus omega, where this is the so-called transition moment. So how well our perturbation connects the two energy levels, and this is the line width or line shape. So two things must happen for a transition to be detected spectroscopically in an EPR spectrum. This must be non-zero, and then the frequency at which we are actually irradiating, so our omega microwave, must match the frequency of this transition. Now, in the original formulation of Fermi-Golden rule, he did not account for relaxation, and so in his case this was a delta function, so unless it perfectly matched, there's no transition. But of course we know from real life that real transitions have a finite width, and so long as there's some kind of match, so long as they're not megahertz away from one another, there will be this intensity. Note, however, that this is the transition probability between level n and level k. In a complete system, we must take into account all transitions between all possible pairs of levels, and so if we are to look at what the spectral intensity actually is at a particular field, we must take a sum over all of these. And so these things implicitly depend on the applied magnetic field. So our spectral intensity at any field B0 would be a sum, so 1 over 4h bar squared, sum over n k, level k, h microwave, level m, absolute squared, gamma, omega microwave minus omega n. It's usually symmetric, so it doesn't matter which way around it is. Up to a constant factor. So that's the total spectral intensity. Let us think about what's involved in here, and let us write down the flow chart of what we need to compute here. So, item 1, for a given value of B, build the primary Hamiltonian. So, for a given B0, build the unperturbed thing. B0 H0 plus H interaction. And building spin Hamiltonians, I've described this in great detail. Please.
I have a question about this intensity. If it's intensity, it should depend on the population and somehow temperature, like on some average.
Yeah, so there would be a Boltzmann factor.
No, this should not.
Well, that's the probability. That's the probability. Yes, the total intensity. Yes, so if you've got some thermodynamics present in here, so there will be Boltzmann factors here. So indeed, the exponential to energy differences in there that modulate these probabilities. I think in the literature it's factored here, but yeah, you're right. Okay, so for a given B0, we build this unperturbed Hamiltonian. We then diagonalize it, we compute the eigenvalues and eigenvectors. So compute energy levels and the energies. Now then, 3 for each pair of levels. So for each n and k, compute n h microwave k. And finally compute the total absorption. So compute A of B0 and 5 repeat us think about what's involved in this calculation. We have a number of different B0 fields in our EPR spectrum. So let's say that's our spectrum. That's how it looks. So that's the B0, that's the A. We have a discretization here with respect to B0. So let's just count the mathematical operations for, let's say, 10 speeches. So there'll be a couple of hundred points, right, of the order of 1,000 points in B0. So 1,000 times. For each B0, we need to build the Hamiltonian, and then we need to diagonalize it. If we have a 10-spin system, it will be 1024 by 1024, so 2 to the 10, the Hamiltonian, 2 to the 10. And its diagonalization will require 2 to the 10 cube multiplications. So that's this here. For all n and k, so there's 1,000 n's and 1,000 k's, so 2 to the 10 energy levels. The matrix vector multiplication scales as O n squared. So here we have matrix dimension times matrix dimension times matrix dimension squared multiplication, so matrix dimension to the fourth. So cube is much smaller than the fourth, so we might just as well ignore the cube and put the fourth power on the overall complexity. And then we need to take the sum, but that's, summation is much faster than multiplication once you've done the multiplications. Now this is roughly 2 to the 10th as well. So we are talking 2 to the 10th to the power 5. That's 2 to the power 50. 2 to the power 10 is vaguely a million. 1,000. So we've got it's 1,000 to the power 5, and that is 10 to the 15th multiplications. Computers typically at the moment, decent computers, about 100 gigaflop, so 100 billion floating point operations per second. So we are talking at, so a gigaflop is 10 to the 9th, 100 gigaflop is 10 to the 11th, so flop per second, and we are talking 10,000 seconds. 10,000 seconds, which is of the order of hours. But it's of the order of hours on a really decent modern computer. EPR spectroscopy has 50 years of history, and you can imagine that even 10 years ago, right, this was a rather dubious proposition. So if we do it naively like this, then yeah, you can kind of do it, but then don't forget that you need to do the powder average as well. So item number 6 here, repeat for all orientations, of which in a typical spherical grid, as you know, there could be hundreds or thousands. Once you multiply this by hundreds or thousands, things start to get seriously busy. And so people have been thinking for a very long time about how to try and reduce the amount of computation at all of these stages. And so what I will roughly go through now is the flow chart that the community has converged on in the last couple of decades as a result of a great amount of work by a great number of people. And I think the best example of a well-implemented code that has all those shortcuts in it, competently done, is EasySpin. So you notice that when you run EPR simulations in there, and in the field swift formalism, they're actually reasonably fast. And I'll roughly outline, now we have absolutely no time to go through the details of how technically such things are implemented, but I will go through at least the general details of how such things are done today. So what was here in the first part of the lecture is how such things would be done naively, as it were, without worrying about how long it takes to compute. But unfortunately, computation's a priority these days. Right, so item number 1, we compute these Hamiltonians inevitably, right? Our task, however, is to compute as few of them as we possibly can. One way of doing that is to generate what's called an adaptive grid in B0. So let's say this is B0, and these are our energy levels. And as you know, they will split around and behave in various strange ways. There will be some crossings and anti-crossings and avoided crossings. And the sampling in places where the levels are well separated can be fairly rough. However, the sampling when there's a crossing or an anti-crossing must be extremely fine, because a lot of things would happen around that place. Abrupt jumps in magnetization and things like that. And so we must find out how to sample this diagram in a way that minimizes the number of diagonalizations. So here we will be digging at that initial factor that I put. So let's say if we put a uniform grid in here, it would have to be extremely fine indeed to sample all those events. But if we make the grid adaptive by bisecting particular intervals, for example like that, then we can sample important regions better than we sample unimportant ones. So how is this done? The standard adaptive grid process does the following. It calculates the energy levels, so the energies at a particular initial grid, but also the derivative. So compute En and dEn by dB0 at some initial grid, which could be pretty rough, and in fact the software packages I've seen, they just take the starting point, the middle point, and the ending point as an initial grid. The question, of course, we know how to compute En, we don't know how to compute dEn by dB0. It's a bit of an involved proof, the so-called Hellman-Feynman theorem. I'll just give you the answer, and the answer is actually remarkably simple. dEn by dB0 is n dH by dB0, and we can, of course, analytically differentiate this extremely easily with respect to B0, so it's just the H Zeeman and H Zeeman n, where this is per Tesla. And somewhat uniquely, I mean, when you look at that formalism, you really don't expect it to be that simple. Second derivatives certainly are not, but thankfully the first derivatives are straightforward. And so we've got the energies themselves, and we've got the slopes at some initial grid here. So if I draw this again, and that will be our initial grid. Now we've got some energies, and we've got some slopes. A collection of energies and slopes is sufficient to draw what's called a spline curve through this data. So what typical software would do is it would subdivide all intervals into two, compute first the spline, so just a piecewise polynomial interpolant through these points, that, and then calculate the midpoints explicitly by diagonalization and see how well they fit the spline. If they don't fit the spline, then the calculations are not lost, because we can actually now do the spline on the finer grid. If they do fit the spline, then the grid is sufficiently good, because it accounts for all the midpoints. And so all the intervals are analyzed on whether this extra point fits the spline passed through the previous points. Those where it does are not refined any longer. Those where it does not are subdivided again. And this, in practice, saves an inordinate amount of time. EPR spectroscopy is really quite special in that most of what's happening is happening around all sorts of level crossings and avoided crossings, and there isn't much going on elsewhere. And so sampling things like this guarantees that you are sampling the important intervals actually exponentially better, because you are subdividing it into two all the times, and the unimportant ones not. The statistics that I've seen from the performance analysis on simulation software is that we are talking about factors of hundreds that can be saved from such sampling. So, okay, we've minimized the prefactor by a couple of hundred. So that shrinks our calculation time a little bit. The second thing we need to do is still, of course, we need to calculate at each of our grid points their transition moment. Because the mathematics involved is linear, the only thing we need to do is we need to calculate those transition moments at the grid points, and then we can interpolate the answers using the same spline. And so our calculations of the A and K and the AB0 are likewise accelerated by the same amount as we have accelerated the number of diagonalizations. So to compute K and H microwave squared and interpolate in a similar way. The third thing that we can use is to avoid this double sum. Think about it. Most differences in energies between the levels would a priori, quite certainly, be very far away from our microwave radiation. If we're radiating at a particular frequency and we're looking at all possible energy levels in the system, well, in fact, most differences will be pretty far. What we are effectively doing is we are computing such resonance fields, so omega and k, energy level difference, implicitly depends on V0. But we would like it for the transition to be important to actually be equal to omega microwave. This is a singularly nasty equation. It's really bad. There are many, many things in how omega and k depends on V0 that are not even single-valued. So the equation's tough. However, once we've done this polynomial interpolation, so let's consider a particular segment here. So this is our energy. And this is our V0. This is one level, how it depends on the magnetic field. There will be some other level here that will depend somehow else on the magnetic field. And so we do have a spline interpolant for this difference, omega and k. At each segment in here, because the spline is a cubic polynomial, it's a cubic equation. So in fact, solving a cubic equation is much easier than solving this entire enormous big diagonalization-based thing. And so we are solving at each interval, so solve cubic equation at each interval. Very, very few pairs of levels, and it would be different pairs of levels in general at each interval, would actually contribute significant transitions to it. That destroys the sign. So this removes from the equation for the overall intensity in them. And the double sum was in fact n by n, where n is the matrix dimension. If the matrix dimension is in the thousands, that's a factor of a million shaded, straight up. And so we are talking, you know, already significant orders of magnitude that we've eliminated from the simulation time by carefully looking and interpolating and carefully sampling and then carefully analyzing what's happening. There are many other things that one could in principle do. So we compute the A in the usual way from here, but there are many other things that can be done that are, you know, happening even before any of that happens. So screening techniques. One thing in particular, that if omega microwave minus omega mk is large, we don't need to consider it. Partially incorporated here again. Second thing, if we are at high field, 3 Tesla, 6 Tesla, 9 Tesla in EPR spectroscopy, that's considered high field because the magnetic moment of the electron is so much greater than the magnetic moment of the nucleus. Then, of course, projection quantum number is conserved. And so the likelihood of any double quantum or zero quantum transitions being allowed is very small. And so we only need delta m equals 1, so single spin flip transitions. Flips only. That eliminates a lot of level pairs from consideration, so we don't even need to think about them. So that shaves off a certain constant factor. And finally, of course, when the user tells us which spectrums they want, they always specify the field sweep ranges. I'm sweeping the field from 3.01 Tesla to 3.02 Tesla. And of course, that's a very narrow range. And if the microwave frequency is spot in the middle of that range, or at some particular interval, most of the transitions would have the energy differences far outside what's realistically going to be hit by that particular field sweep. So, field of view pruning. Maybe another order of magnitude or so. Finally, let's say we shaved off 6 or 7 orders of magnitude from the calculation time. We come to the powder averaging problem, and thankfully, again, because analytical derivatives exist with respect to the orientation parameters, angles, and so on, the same kind of adaptive grid procedure can be done in 2D for the theta and the phi spherical angles, and it can be adaptively refined and adaptively sampled. And so instead of thousands, tens of thousands of points, you can shake it down to a couple of hundred points if you like. So all of that results in the ability to compute EPR spectra of common spin systems in a matter of seconds to minutes. One thing that is quite important is that all of this only works if the core assumptions that we have made about our experiment, that this is just simply the system with a static microwave shining on it at a static frequency, and the Hamiltonian that doesn't depend on time, except in the microwave part. So this is the most basic field-swept EPR experiment. As soon as we are talking about DEER, as soon as we are talking about any pulse stuff like Andor, high score, and so on, this no longer applies. You have to redo the entire process for the flow charts of those experiments and cut a lot of corners and so on. So these extreme time savings do not generalize. Every time you have a new experiment, you have to do it, if it's even possible, which it usually isn't, all over again. So this is the core difficulty with this field-swept picture in that, well, fundamentally it's still exponentially scaling because it's 2 to the n somewhere. You can shave off constant factors, but eventually, Mother Nature catches up with you. Right, so one important thing that again is different between NMR and EPR. Those of you who did simulations of solid-state NMR will remember the concept of a spherical grid. And that a great amount of time and effort has been expended by very illustrious people over the last 30 or so years in trying to find the optimal grid and so on. There's a good reason for that, because such an analytical based subdivision and interpolation process is only possible in systems that are what's called spherical low rank. That is, if you plot the spherical angle dependence of your answer in terms of spherical harmonics, these harmonics are low rank. And this is always true for Hamiltonians. So if we draw our Hamiltonian, for example, the interaction Hamiltonian, as a function of some orientation parameters, it would have the part that doesn't depend on the orientation. H0 or H iso, the isotropic part. And it will then have a part that does depend on orientation, and people usually express it in terms of so-called Wigner functions. They're just convenient functions of the angle, in the same way as sines and cosines are functions of the angle. So we would have a sum here, or one indices k and m, from -2 to 2. HKM, some constant matrices, D, these Wigner functions, bunch of trigonometrics really, Km of those angles, omega. And this dependence in terms of angles is very, very smooth, because the Wigner functions are low rank. Typically what you'd see is, well, the worst of what you'd see is something like this. It's plus, minus, minus. It's a typical second rank spherical harmonic for a Wigner function. So this is smooth. And harmonics of spherical rank, of different spherical ranks, differ in how sharp they are. The greater the rank, the sharper they become. If you remember, in our ordinary time domain magnetic resonance, we always had exponentials of these Hamiltonians. So it was x minus I h t. That was the fundamental object which we had to do. And that, of course, is a Taylor series. N0 to infinity minus I over factorial minus it to the power n, h to the power n. Which means we must take nth power of that, and if we take a product of Wigner functions, one of rank A and the other of rank B, the result will be a linear combination, but it will be from A minus B to A plus B. So up to dA plus B. So ranks increase, and because the series is infinite, they would increase all the way to infinity, the result being that the exponential of minus I h t would have all possible spherical ranks. So the large sum L0 to infinity, sum over k and m. Some coefficients, matrix valued, C, L, K, M, and Wigner functions of all ranks, K, M, of omega. And then that's a problem, because if you look at D100 or D couple of 100, 0, it looks like an extremely sharp needle with extremely sharp needles sticking out of this and another sharp needle pointing down. And if you've got a linear combination of such things, they're absolutely not smooth. And then you need hundreds and thousands, tens of thousands of points of spherical grid to integrate.
Sorry, I can't quite see the notation. What's the first thing after the second sum? Is that a C?
It's C, just some arbitrary matrices, which are very hard to compute as well.
Why do they have a hat on?
They're operators.
Okay.
And these are scalars. The point is, when you exponentiate a Hamiltonian, the spherical angle dependence of the exponential is extremely sharp. And this is the source of all our problems with spherical averaging in NMR. In EPR, this rather weird flow chart that we've got has one extremely significant advantage. Hamiltonian is low rank, so smooth in spherical coordinates. So this is shown. But the eigenvalues and the eigenvectors, when you do a similar decomposition in spherical angles, there's most can be interpolated. And so one of the remarkable efficiencies, I cannot say more without going into an even scarier technical detail here. One of the primary efficiencies of this eigenvalue, eigenvector approach using the Fermi-Golden rule to computing field-swept EPR spectra is that you can interpolate the energy levels, like I've just described, to save a great deal of time, but you can also interpolate orientation dependence of the few parameters that you need, because you only have the intensity for each transition as a function of the angle, and you've got the frequency of each transition as a function of the angle, and those you can simply interpolate with a spline and then integrate the spline. And so this is why when you are using EPR simulation software, often you would see an unnaturally rapid power average. You'd compare it to what you'd normally have in NMR, for example, 2 or 3-dimensional solid-state NMR, when you have to painfully trundle through a finite spherical grid, and you think, goodness, how could they possibly compute the spherical average so fast? And the answer is that's because the principal objects of the field-swept formalism are the energies and the energy levels, and their low rank, low spherical ranks. And the principal object in NMR spectroscopy, because we're always in the time domain, is the Hamiltonian exponential, and it's always a high rank object. So this needs much smaller spherical grid and is much better behaved than what we are commonly doing in NMR spectroscopy. Okay, that I think is that's it for today. So sorry I couldn't go into the nitty-gritty of any of this, but the summary is the simulation of field-swept EPR spectra basically follows, with a few tweaks and efficiency improvements, the standard textbook perturbation theory.